engineers, analysts, low code, no coders? Welcome back. We've been making great progress on our multi-agent Postgres data analytics tool. Over the past 3 videos, we've built out a multi-agent framework on top of AutoGen, GPT-4, and a couple new patterns we built from scratch on the channel. We created the orchestrator as a way to manage our agents, and we obtained full control over our agents with specific multi-agent conversation flows, like the sequential and broadcast conversations. We can type in natural language, and our 2-team multi-agent system will get to work for us, generate SQL, run it, and present results to us. This is fantastic. We're pushing into a new field of agentic engineering, and that brings us to this video. Our multi-agent Postgres data analytics tool has one major problem. It's only reading 2 Postgres tables. If you've worked on any production database, you know that you're often operating on 10, 50, and potentially hundreds of tables with over hundreds of thousands and millions of rows. This renders our Postgres agent effectively useless, and that violates a major tenet and principle of what we do on this channel: build valuable software. So let's make our Postgres agent valuable again by giving our system the ability to focus on tables specifically relevant to our natural language query. We'll also add token count and price estimating so that we know how much we're spending on GPT-4 throughout the life cycle of our orchestrator and our agents. As overwhelming as it has been, I've really been enjoying reading everyone's comments, seeing what you're thinking, what you're building, getting feedback, and hearing people complain about the captions at the center of the screen. So at the end of this video, we'll go over a couple of the most popular comments, like where's the code at? Can you use local models? And a few more. Stick around if that interests you and you want to be a part of the conversation. Now let's refocus on managing our Postgres multi-agent memory and costs. All right, so let's crack open VS Code and let's review what we've done so far. I'll start by running an example, and what we're gonna do is we're gonna get all users with the enterprise plan. So again, we're typing in natural language. It's going to hit our agent pipeline, and then we'll get the results back from our Postgres database. Let's go ahead and run this. So just as before, we have the table definitions at the top. We're then passing that prompt and the results that flow between 2 teams, our data engineering team and our data visualization team. Our data engineering team is responsible for generating the SQL and running it, and our data visualization team is responsible for reporting the results to 3 different files. Fantastic, so our agents just completed. We can look at the responses. So you can see here we have 1 result with the enterprise plan in JSON format here. We have it in text format, and we have it in YAML format. That's thanks to our data visualization team. So let's quickly look through our code. Just as before, we have 2 environment variables: Postgres database URL, OpenAI key. We're pulling our table definitions. I'll explain the mock suffix at the end in a moment. We're building out prompts. We're building out our OpenAI configurations and our function maps for each one of our agents. We have our prompts for our data engineering team. We then have our orchestrator that we built in the previous video. And then we're running our data engineering team using the sequential conversation type. After they complete, we fetch the SQL result from their messages, and then we pass it right to our data visualization team, which represents a team that reports data to files. That's just a high-level review of our application so far. Check out the previous videos in the series if you want to get fully caught up. I've been a little deceptive at the beginning of this video, and I want to show you why exactly. As you can see, I've added up to about 100 new users in our user table, and on the side here you can see I've generated about 50 tables to better represent a production-like Postgres database. If we hop back over to the code and jump into this get table definitions, you can see that I've basically just mocked out a string that happens to be our previous create table responses. We're no longer dynamically fetching this out from our database. And even the prompt I specified here is a bit deceptive because the only user with the enterprise plan is Alice, and there's only 1 of these, right? So if we sort these and look for enterprise, Alice is the only one with the enterprise plan. So I basically completely avoided what I like to call token explosion, or when you exceed the available context window for your LLM. In this video, we're directly addressing this issue. We're gonna make a few major changes to our code base. So let's get to it. The first thing we need to do is reorganize the code base. It's getting a little sloppy, it's getting a little unwieldy, it's kind of hard to read. So I'm going to do a little bit of code refactoring right now. As usual, I'm going to skip through this to save you time. Fantastic. So I've just refactored our code a little bit. We now have two new modules. We have a directory called agents outside of the modules directory. Inside of agents, we have the agent config and agents.py. So let's dive into those and see how we've broken things up. At the top level, main.py is now just this, right? It's about 68 lines, pretty clean, instantiating our variables, pulling out the prompt from argparse. We're still building out our table definitions. We set up our prompt, but now we're setting up our teams like this. We call agents.build team orchestrator. Very clearly, we're building a data engineering team. We're making them run the sequential conversation, getting the result, and we're passing that along to the data visualization team, right? Let's see how we've broken this down. Inside of agents, so inside agents, we now have all of our prompts right at the top. We then have all of our agents with a special build function for the senior analyst since it needs the context of the Postgres database. Then we have our orchestration. And the orchestration is as simple as this. You simply pass in a string and the database, and then we build out the appropriate team based on the team name. So you can see here we have support for two different teams, the data engineering team and the data visualization team. In the last file, we have the agent configuration, which builds the appropriate configuration for each one of our custom agents functions that it needs to run. And then we just broke things apart a little bit, creating a couple helper functions to quickly create the function maps that we need and handle special cases like needing the database Postgres manager to create the run SQL function map. So this is super nice. It just cleans things up for us a whole lot and makes the program a lot more understandable. So this is a great place to kick off our next task, which is to filter out the tables we're running. Let me go ahead and rerun the same example so we know our code's working, clean up some bugs. Great, so this ran perfectly just as before. Now I'm going to light a dollar on fire to showcase the problem of LLM memory by querying without the table mock function and by using a natural language query that will return even just 50 rows. I'm going to replace this. We're going to get our old get table definitions for prompt, which is going to pull all the tables from our Postgres database. And remember, we now have some 40, 50 tables. And instead of reusing this prompt, I'm going to do something more detailed. So if I want to, for instance, fetch all users with the example.com domain, let's do that. Give me all users with the example.com email address. And now I'm going to run this. So right off the top, you're going to see a ton of tables come into our prompt, right? This is all going into a single prompt, and we haven't even run a single agent. Okay, so right away we got this model's maximum content limit is hit. This is the problem we face, right? We can't actually do anything interesting with our agent in this current state. So we have to do two things to resolve this issue. We must fetch only tables relevant to our natural language query. In this example, we only really need the users table. And then second, we need to refactor our application and our agent pipeline so that we don't process the returned results through any OpenAI request. Right now, I'm going to build out a brand new embeddings module to help us embed our tables, and then we're going to do a similarity match against all existing tables. Let's code this up right now. We now have a brand new database embedder class. We're gonna run poetry, add transformers, torch, scikit-learn. To count our tokens, we're gonna use tick token. Great, so we now have that installed, should be all good there. Now let's look at our database embedder class. So we load the models and we create two mappings. Remember, what we're trying to do here is filter out the tables we don't need for our natural language queries. In order to do this, we have this add table method. This add table method takes a table name and it takes the text representation. It's the SQL create statement for a table, which details all the columns that our tables have. And then we're going to compute the embeddings. So you can see we have the compute embeddings function here. I'm not going to go into a ton of detail with computing embeddings. There are tons of videos already that do that. that, pick your favorite embedder, and then build out the text to embedding function and also your cosine similarity function or whatever the equivalent is that you're using. But basically we have the add table function, which is going to create a map between the name of the table and the computed embeddings. After we have that, we can run get similar tables via embeddings, which takes our natural language query, converts it to an embedding, and then it runs through each one of the tables we have mapped as embeddings and compares them. So this compares our natural language query as an embedding to table definition as embeddings. And then we'll get the sorted values from most relevant to least relevant. If we hop over to the top, I'm going to do a little test here. We have a return statement to block out the rest of our code. Inside of our database module, I created one new function. It basically just gets a map between the table name and the table definition. We then build a new instance of our database embedder. We add every table to our embedder. And then here, I'm just printing out the name to the embedding so it's super clear. And then the final key line, we take our raw prompt and pass it in to get similar tables based on the prompt. And then we'll print out the similar tables here. So let's go ahead and run this. And what we should end up with is a list that contains tables relevant to this prompt. Okay, so you can see several interesting things happen there, right? First off, we have a massive list of embeddings. So I'm gonna go ahead and just remove that, rerun. You can see here we're adding the tables to the embedder. And now we have our list of similar tables. So we got order details, we got suppliers, and we got user profiles. A couple things to notice here. We don't have our users table, right? Our embeddings gave us 3 tables, none of which is our users table. Looks like we're getting relatively close. And if we dig into the table definitions a little bit for order details and suppliers, we can see that we didn't really get anything related to the user from order details. Let's go over to suppliers. So kind of tricky here. In suppliers, we do have email. So you can see why our embeddings would match against this. If you look at the user profile table definition, you can also kind of see why. We have user ID and we have address. If we look at our natural language prompt again, you can see we have the word users. You can see we have .com and then we have email and address. So address also got picked up there. So what can we do about this? We're actually completely missing the users table, which we need to query on. So let's make a couple tweaks. In our get similar tables via embeddings, we have an integer here that specifies how many tables we want to pull in due to the similarity, right? So let me go ahead and just bump this to, let's just say, 10 tables. So let's bump to 10. Let me remove this add line and let's rerun. Let's check out our list. We now have order details, suppliers, user profiles, product reviews, product images, several other tables here. Again, still no users. Now, there's a couple different routes you can go here. We can increase this even more and hope that we get some more accurate results. We can look at a different embeddings method and technique, but I'm gonna do something a lot simpler. Notice how within our string, we're actually specifying the table we need. We can kind of just hack around this entirely for our specific use case and build kind of a fallback / workaround where if we see a table name in our query, just pull the table name in. Let's code that up. We now have 2 new functions in our database embedder class. Let's take a look at them. We're now doing this really simple, kind of intuitive word match against all tables inside of our embedder by basically taking the table name and looking inside of the query to see if the table name exists there. If it does, we're adding it to a list in which we return. We then have one more function which combines both the embedding and the word match results into a single table. We also updated our via embeddings function to return just the table name and not the probabilities. On the top level here, we're running the same code. We're getting all the tables as a map from our Postgres database module. We're building out our database embedder. We're adding each table so that it can be embedded. And then we're running our new get similar tables function, which runs both the word match and the embeddings. We can now drop our n equals 10 down to something like 5. And let's run our query again. So give me all users with example.com email address. Let's see what tables we get back. So awesome, we get 5 tables, and then we also have users at the end here. We have users because we specified it exactly. So there's definitely an argument for just doing this word matching. I'm going to leave the embeddings in. I think it's useful and it's a good technique to know when dealing with string matching for LLM memory and for other applications as well. Now that we have this functionality, what we can do is add one more function to our database module that, given a list of tables, we want to get those create statements. Awesome. So now we have the full flow to get our reduced list of table definitions. So let's go ahead and run this one more time. Sweet. Now we have our users table and a couple auxiliary tables. We can increase and decrease this get similar tables value. Just in case that doesn't work, just in case it's not getting picked up, we can specify exactly the table we need in natural language and it'll get picked up. Let's run one more query here. Give me all the users with jobs that have been completed and let's look at one more table here. Let's get job tags and their job tags. So just to test out this functionality, we should now get perfect the jobs tag table. We also have the jobs table and we also have the users table. That's how we can manage our table definitions coming into our application flow. So let's reconnect our application here to run the full flow given our new table definitions string. Instead of using our old method where we get all the tables, we're now going to get a set of filtered results and then we can continue with the original flow of our application. And if we run this on a smaller size example where we're just getting, let's say we want to get users with the gmail.com email address with jobs that are completed. So let's go ahead and reconnect this, and I'll probably break this in the middle because we know our agent system works. I just want to get that top level working so we can see a SQL query get generated. So we got the tables necessary, right? We have the users table and our jobs table, and bam, that's perfect. So let's scroll back up. You can see the SQL that got generated is this user select, and we're also going to get job ID, job status. We can see that we're doing the proper query here. We got the user's email like Gmail and the job status completed. So awesome. So now we have a reduced list of tables coming into our application. So let's go ahead and add a token counting system so that we can better understand how much each run of our Postgres data analytics system is going to cost us. Okay, we now have a new function in our orchestrator called getCost and tokens. As you can see, it returns both the cost and the tokens for that given team within the orchestrator. Let's dive into this method here. All we're doing here is calling into the LLM estimate price and tokens, and we pass in a string to that. We're doing a little bit of string parsing from our orchestrator agent's messages, from that list of messages that we built up over the conversations that we have. This is why the add message is important, so we know all the conversations that have been had. And then we're doing, inside of the LLM estimate price and tokens function, we're doing a really rough price calculation here. I like to round up. I like to be really safe on how much is actually getting spent. GPT-4 is currently costing 6 cents per 1,000 tokens for the output, and about half for the input. So, the prompts that you send in to OpenAI's GPT-4 cost about 3 cents. The output costs about 6. I'm just rounding up. I frankly prefer being, conservative in my estimates. Things always just work out better that way. You end up saving money in the long run if your models are projecting higher costs than actually are. You can definitely get more fine-grained and detailed with this. Basically, we're just using the tick token encoding on all of our text. I'm then taking that and converting it into actual costs, dollar costs based on 1,000 tokens and the price of GPT-4. Specifically, I'm looking at the output tokens. Now we can run fix this, organization. Now we can run both teams and we can see, how much is it costing to run each one of these teams, and we can see how much it costs to run our multi-agent system as a whole. Again, we're going to run a safer prompt that's not going to token explode our system. It's not going to give us an overflow breaking the context window. Switch this back to just enterprise users. So we're just going to get that one user so we can just look through and see if our pricing functionality is coming through. All right, our YAML agent is wrapping up its write to the YAML file, and then we should get our token cost. Great. So as you can see here, the orchestrator was successful. That's the data visualization team finishing up, and it looks like this run cost us about 5 cents with a total of about 900 tokens. We can see the data eng team costs 2 cents, and the data viz team, wow, data viz team costs 3 cents. I'm going to have to let the staff know they're really chewing up, eating into our margins. No, this is pretty cool though, right? So, and then we can see the total organization costs, right? This is really important. You want to be understanding whatever system you're building with LLMs. I highly recommend you build this. Don't just blindly blast out cash to OpenAI. They are the best in the business right now. I'm going to continue using them. I'm going to continue, frankly, throwing money at this, but you also just want to be aware when you're really blowing things up. It also helps you write better prompts when your prompts only have the information they need to complete the job you've requested, right? So there we go. We're building out some more functionality to help us create more sustainable, more aware modules. And now it's time to deliver some bad news. Now we need to make sure our agents are never exposed to the possibility of thousands of rows from our SQL query. It's time to put our manager hat on. It's time to do the hard job. It's time to let go of some of our employees. It's time to let go of some of our agents, right? The orders come in from upper management. The cost for the data visualization team is just too high. It's time to fire our data visualization team. Let's downsize our agents and update our run SQL function to run and report the results directly to a file to prevent token explosion, to prevent exceeding our GPT memory window. There are tricks and methods we can use to tap into the SQL response. We can use techniques like random sampling to take a peek in and grab just a couple items for our agents to look at, but we'll explore that in another video. Inflation's hitting. It's time to make some cost cuts. It's time to act like a big tech company. We gotta make the cost cuts. Data visualization team, it's just gotta go. Okay, that was pretty tough to do. I just fired our data visualization team. That was hard, but here we are. We now have just our data engineering team, and we've now put more responsibility on our senior data analysts. Really kind of key employee. That run SQL function is now writing those results to a file, and then reporting successful delivery to the product manager. So let's go ahead and now run a larger response and see what our organizational costs are, and let's see what the results look like. So let's go ahead and look at one of those larger queries. Let's go ahead and look at example.com email addresses. Let's also look at this feedback table and make our query even more complex to really see what's going on. So I want to also get with ratings above 3 users with example.com email with jobs that are completed, and let's make sure we get that completed right with the casing. I believe that was, let me just add quotes around that, make that uppercase C, and with job tags, job feedback with ratings higher than 3. Okay, so there's a decent amount going on here. This is, 2 joins, a couple of where statements. Let's see how our new trimmed down team does, and let's see how much this costs to run. Let's go ahead and fire off our refined Postgres multi-agent system. Okay, so we got the job feedback table, we got the jobs table, and we have our users table here. Great, so it looks like that join statement came through. Fantastic, this looks really good. It's hard to cut costs as a business owner. It's hard to cut costs, but it's really great to see when it works out. Let's go ahead and look at that results file. Fantastic. There's 2,000 characters here. Let's go ahead and go to the OpenAI tokenizer. We can see that 800 tokens were used here in this response. We want to make sure that our agents saw none of that so that we save costs as we're operating on our Postgres analytics tool. So we got 800 tokens here. If we look at our actual tokens seen, we only saw 400. So, throughout the entire application run, we only saw a total of 400, which yielded a organizational cost of just 3 cents, right? All in all, this is pretty good. 3 cents running a query like this. It got us the correct results. We can see we have strictlyexample.com email addresses here. And if we wanted to do more validation, we could pair them up and run that exact query. The nice part about this functionality, and I think we'll want this in some of the versions that we're going to build out, is we can also just return this query and run it and modify it. Even if we don't want all the results given back and we just kind of want help working on a query, building out a query, or we want to, make modifications to a query, we can just hop in here and make that happen, right? We can just pull this out. This is great. So let's run one more larger example. Let's say I want to get all my failed jobs, right? Let's do some job analysis. Let's get all failed jobs. Show me all failed jobs. And again, to activate our word matching against our table, we're just, directly referring to the jobs table here as it's named. So we're going to get all failed jobs. Doing some data analytics here. I want to see all the failed jobs that are harming our feedback. So I want to look at job feedback with ratings less than 3, with job feedback that have rating less than 3. Present the rating alongside the job. Okay, let's go ahead and run that. So our data engineering team is leaner, it's faster, it's got some upgrades, have some new reporting capabilities. Nice, there's our statement there. Job rating feedback less than 3, good. And okay, so let's look at what happened here. It looks like we got nothing at all. So let's make sure that everything looks good. Status equals failed. I'll bet we have that same issue. Yeah, so this is something that can be improved. We need to specify the exact casing of status. And let me just get that quotes, failed jobs. Let's go ahead and rerun that. So nice. Let's take a look at what happened here. So the query that was built, kind of nailed it exactly. So now we're getting all the job IDs and their job rating. So nice kind of trimmed down example. And we're also getting the SQL back. And you can see the token usage, again, really low, really lean, with just 2, 3, 4 agents. Although we did fire our data viz team, we still have access to them whenever we need to, if we want to, make a rehire or, use them, down the line for anything. We still have that. We still have the pattern. We still have all of the conversation flows to build out, any arbitrary team of agents, right? So again, I want to emphasize that idea of building blocks. You orchestrate your conversations, your agents, your prompts. Keep collecting, keep building, stack these up, and eventually what you're going to end up with is a really cool built out complex system that can solve problems that before were not solvable. So this is awesome, guys. We can now run our Postgres multi-agent application on a database with 50 or hundreds of tables without worrying about hitting our context window. And even if similarity search doesn't get the records we need, we can specify the exact tables by calling them out by name. We also have a nice token counter. So we're getting the price, we're getting the cost of our agents. This is really turning into a more full-scale product that is usable in production systems. What's next? Where do we want to take this? I think we can do a couple different things. For sure, we need to get this application behind an API so that we can call this from a clean user interface. We can start to imagine a front end where we type in natural language, we get both the SQL query and the results, in varying formats based on the size and the number of rows returned. We're talking tens of thousands of rows. Maybe we just return a CSV, but if we get something less than that, the front end can handle that. It can, show a nice clean table. So, in the next video, we'll be looking at that. We'll be looking at how we can build out different teams without blowing up our context window with a token explosion. And we're looking at ways we can improve our system, utilize our agents, utilize our conversation flows while monitoring the costs on our system. A lot of this has been done already, but this is important. This is one of those stepping stones that's really important, and I want to kind of, make it really obvious for you guys when you're building out your agentic systems. You need to monitor your costs, and you need to be able to really use your application, be real with the limitations of LLMs, right? Memory is a huge limitation right now, so we have to work around it the right way. If you can get away with simple techniques, absolutely use them. I know there's a big wave of using embeddings on large documents. That's definitely going to be important. We'll likely touch on combining PDF documentation, large docs with your database, since that's what a lot of product data analytics work has to do with. You're looking at documents, you're comparing reports from companies, you're looking at reports from statistical analytics, and then you're combining it with your own Postgres database, the information you have in your database. So that can definitely be something we look at in the future. Before we go, let's discuss some of the top comments from our multi-agent series so far. Where's the code at? Long story short, the code is coming. It's been evolving a lot as we push this through week by week. It's evolving, it's changing, and I want to ship a version of this code to you guys that is stable, that is helpful, that is useful, and really easy to understand. I'll definitely be sharing what we built on this channel so that you can use it in your own work, building your own agentic software. I just frankly haven't had time to really formalize this code base yet. I want to make sure that we're at a more complete version that is stable and consistent before I release it to you guys, because I want it to work. I want it to work for your use cases. Okay, next question. Can you use local models? This is a good question, but I think it's not the right question. I think the question should be, should you use local open source models? And right now, the answer to that is no. Why shouldn't you use local open source models? They're not even close to GPT 3.5, let alone GPT-4. GPT-4 is in another galaxy compared to the performance of GPT-3. Currently, at the time of releasing this video, all open source models are far behind GPT-3 and very, very far behind GPT-4. I can talk more about this in depth if you guys want. And I know it's not a popular opinion to be like pro-centralized companies that are gatekeeping their models, but they're running a business, and frankly, OpenAI, Microsoft, they're running a great business. Just to reemphasize, as part of the principle set on this channel, we use the best technology for the job. That means when it comes to building agentic software that writes code for you, software that does marketing for you, software that does data analytics for you, right? Just like we're building right now with our Mult-Agent Postgres system. Right now, that means using GPT-4 from OpenAI. Why? Because it is the best in the business. This is the series that we were all hoping for. The other YouTubers just go over toy examples. I love your focus on building powerful, valuable pieces of software. I really want to say thank you for saying this. Thank you to everyone that's liked the comment. It makes it clear that you guys are also, huge fans of this. I often find myself frustrated with the existing engineering tech YouTube channels because they're typically discussing like really high level things, which is, it has some value. But when they dive into code, it's usually rehashed, pre-existing toy examples, usually from the documentation of the tool. If I wanted a pre-built example, I just go look at the docs myself, right? We can all just go look at the docs. We don't need you to do that on your channel, right? That's part of why I started this channel. I wanted to go deeper. I wanted to build real valuable software. And I thought it might be interesting for other engineers to see what that really looks like and to get and share ideas. So I'm really glad you all are here. I'm really glad you're all interested in that. You can expect unique, valuable pieces and chunks of software for my channel in every video. We'll skip the rehashed toy examples pulled right from the docs. Other channels have that handled. More AutoGen. You got it. Put all prompts in one file. So this is a really great approach. I'm definitely behind this, definitely recommend this. When you're building out more complex prompts, you have to build out string templating when you have variables that you need to insert into these prompts. But definitely storing up a huge library of prompts in text files is a great idea. I've been working on a unified solution for sharing prompts. I'll share more on that in the future. This is low-key the most important channel on YouTube. Wow, this is a really huge, really bold comment. I think, although this is one of the best comments I think I'll likely ever see, I think what's even better than that is the 21 likes that this comment has. To me, it shows that you and others understand what we're doing here. The immense value that can be created when you build software that operates on your behalf in parallel to you. I truly believe that this idea is the most valuable thing happening right now in software. Once you get your agentic software online, you get one of these online, you get two of these online, you get three of these online. Working with you in parallel, the value you're going to be able to create will be like none other. We're not talking about 10x, we're not talking about 50x, we're talking about crazy numbers that we cannot imagine. Why? Because you'll be an agentic engineer who has seemingly living software executing on their behalf. So with that context, and I really believe that this viewer and the 21 people that thumbs this up understands that, with that context, is this low-key the most important channel on YouTube? Let's find out. Like, sub, hit the notification bell. I'll see you in the next one.